class. Today we're going to be talking about section 6.23, which in AP Stats is comparing means. So we're going to do inference, two-sample hypothesis test for the difference of two means. We'll also look at a two-sample confidence interval for the difference between two means. So the first thing we want to do is just review our sampling distribution of the difference between two means, x1 bar minus x2 bar. Is that the mean of the difference between the means in our sampling distribution is equal to the difference between the true population means mu1 minus mu2. Now remember, a sampling distribution is a theoretical model. So it's if we get all possible samples in existence, then our mean of all of our sample mean differences will equal the difference of the true means. Our standard deviation of the difference between our two sample means is the square root of the standard deviation of the population for the first variable squared divided by n1 plus sigma sub 2 squared divided by n2. And these are on your formula sheet. If you look at the sampling distributions for means section for two populations, you can see the formulas there. All right, so if you have your formula sheet, it's always a good idea to get it out and kind of roll with me here, because sometimes we look at the tables, things like that. Now, the sampling distribution of x1 bar minus x2 bar is approximately normal if n1 is at least 30 and n2 is at least 30, or if the sampling or if the corresponding population distributions are normal, then we can assume that the sampling distribution of the differences is also approximately normal. All right, so a two-sample hypothesis t-test for mu1 minus mu2. Now, I've done a few videos now with hypothesis testing. So if you're just jumping into this one, you might want to go back and watch a couple of them. I'm going to move a little faster through these, hopefully. In general, when we test a claim about the difference between two population means, we have the following null and alternate hypotheses. The null is always that mu1 minus mu2 is equal to 0, or that mu1 equals mu2. It means that they're the same. And then our alternate would be any combination of them not being the same. So mu1 minus mu2 is greater than 0, which is also like mu1 is greater than mu2, and so forth. The degrees of freedom in this case, so we're going to be using our t-tests because, and if you don't remember, we use t when we don't know our population standard deviations. And I should say and here. So if we don't know sigma sub 1 and sigma sub 2, we're going to use t. And in order to use t, we need degrees of freedom. Now, with our one sample tests for means, our degrees of freedom was n minus 1, the sample size minus 1, but it's not n minus 1 when we have two samples. Technically, you can get away with it, but your math isn't going to be accurate. So what you want to do is use the degrees of freedom value that your calculator gives you, which is when we run our two-sample t-test in our calculator, it'll tell you a degrees of freedom value. You'll want to just write that down and use it. So our conditions for a two-sample hypothesis t-test for the difference between the two means, the first one is always randomization. We want randomization. If we don't have it, then we just assume that our samples are good representations of their population. Second one is that we need independence within each sample. We can use our 10% rule or context. And then 3, our sample sizes are large enough to assume that the sampling distribution of the difference between our two x bars is approximately normal. So we can, again, figure out if our sample sizes are at least 30, or if they're not, we can show the nearly normal condition, which we've talked about previously, for both samples. So two displays, I usually use histograms are required. We went over the nearly normal condition previously in a different lesson. And we need independence between both samples. I usually just rely on context for this one. Sometimes you can rely on randomization as well. All right, so example 1. A farmer suspects that pigs fed one diet, which is diet A, have a larger mean weight gain than pigs on another diet B. 72 pigs, so we have 72 pigs, of the same weight are randomly assigned to one of two different diets. The mean weight of each group after 6 months is given below. determine if there is statistical evidence that validates the farmer's suspicion. So he suspects that diet A pigs will have a larger mean than diet B pigs. All right, so first we need to define our parameters. Mu sub 1 is the true mean or the population mean weight gain in pounds of pigs on diet A after 6 months. Mu 2 is a true mean weight gain in pounds of pigs on diet B after 6 months. We have some statistics here on the side with our N, number of pigs, our X bars, and our S's. Now, our null hypothesis is that mu1 minus mu2 is going to be equal to 0. So that means that the diets, well, one isn't going to be better than the other necessarily, or at least not what he's saying. So he says he suspects that diet A is going to have a larger mean. So he's suspecting that mu1 is going to be greater than mu2, or mu1 minus mu2 is going to be greater than 0. So this one is actually less than or equal to in our null hypothesis, even though we show it as equals. Technically, it covers less than or equal to. It has to be the exact opposite of the alternate. And in our alternate, so this one supports the farmer's suspicion. All right, and then the other one doesn't. Now our conditions, again, we always want to name our test. So it is a 2-sample t-test for mu1 minus mu2. Our conditions, the first one, it was stated that we had randomly assigned the pigs to the diet. 2, it is reasonable to assume that 36 is less than 10% of all pigs on diet A, and 36 is less than 10% of all pigs on diet B. Thus, independence within each sample is assumed. Random assignment implies independence between the sample groups. So if they're randomly assigned, you can assume that they are independent of each other. And the fourth one, we have n sub 1 equals 36, which is at least 30. And n sub 2 is also 36, which is at least 30. So the sample sizes are large enough to assume the sampling distribution of x1 bar minus x2 bar is approximately normal. All right, so now we get to do our mechanics. So the t distribution, we're going to have the difference of our sample means. So kind of go back up here. My sample mean x bar sub 1 was 55. The other one is 53. So I'll have 55 minus 53 minus 0 from our null hypothesis divided by the square root of our standard deviations were 3 and 4. So 3 squared divided by 36 plus 4 squared divided by 36. And I can plug that in my calculator and I get 2.4. Now, you can also use your calculator. We need to use our calculator anyways at this point to get our degrees of freedom. So my suggestion, so you don't forget to write down your degrees of freedom because you will lose points. As soon as you write T equals, underneath it, write DF equals, just so you don't forget before you get all into the problem. Make sure you put that on your paper. We're going to go to tests. So stat, and then over to tests. And then we are doing a 2-sample t-test. And I'm going to put stats in it. I don't have data. I don't have a list of data, but I do have the stats. So my x sub 1 mean is 55. My S1 is 3. And my N1 is 36. I've got 53 for my mean for my second one. I have 4 for my standard deviation and 36 for my N. I want mu1 to be greater than mu2 for my alternate hypothesis. Pooled, no, just don't do pooled, and then calculate. All right, so here I can see my t-value of 2.4. I also see my degrees of freedom, which is 64.911. My alpha level, which they did not give us any information. So I'm going to say it's 0.05, and I'm going to write assumed underneath that because we just kind of made it up. Usually I assume 0.05. And then we want to do our probability. So if my t-value is 2.4, I want the probability that t is greater than or equal to that. So probability that t is greater than or equal to 2.4. And then we can see here from our computer output that probability value, 0.0096. Now, if you were using your t-table, it's a little difficult to use a t-table to get the p-value. I usually don't do it because you can't really get super accurate. The calculator will give you more accurate values. But the way it works is if my degree of freedom is approximately 65, I go on my t-distribution all the way down, and then it starts skipping. So the closest I can get to 65 is really where it says 60. And then I'm going to go over until I see something that's as close to my t-score as I get. My t-score was 2.4. So if I go from 60 degrees of freedom over until I see 2.40 or 2.390, that's as close to 2.4 as I can get. The tail probability up at the very top is 0.01. Now notice this one, if you had put the probability that t is greater than or equal to 2.4 is approximately 0.01 using the table. Notice it's pretty close to actually what we got in our calculator. 0.0096 is close to 0.01. I usually use the calculator value, but you can use the t-table. It's just a little tricky sometimes. All right, so in conclusion, since our p-value is less than alpha, or less than or equal to alpha, I should say, we reject H naught. So if we're rejecting H naught, so go back up and look at what H naught was, and this is why when I write my hypothesis statements, I always kind of write in parentheses which one supports the claim. And so H alternate, the alternate hypothesis supports the farmer's suspicion. So if I'm rejecting H naught, then I can support his suspicion. So thus, we have sufficient evidence to support the farmer's suspicions that pigs fed on diet A have a larger mean weight gain than pigs fed on diet B. All right, so next we're going to look at a two-sample t interval. So we're going to look at the confidence intervals for this scenario. So we have our formula here. We have our difference between the two statistics, x1 bar minus x2 bar, plus or minus our t critical value times our standard deviation in terms of our sample standard deviation, because we're never given population information if we're doing a confidence interval. It has the same four conditions needed that we just went over. And again, you're going to run your test to find your degrees of freedom in your calculator. Given below are saturated fat content in grams for randomly selected pizzas sold by two national chains. Estimate the difference in mean saturated fat content between the two chains with 90% confidence. I wrote in here, assume all conditions were met. Just based on time in our video, I didn't want to have to go through all of them. Determine if your interval supports the claim that the mean saturated fat content between the two chains is different. All right, so the first thing we need to do is go into your calculator, go to edit, and you need to put these numbers into the list. I've already put them in here, so you might want to pause the video and put those in your list. Next thing we want to do on our papers is make sure to define your parameters always. So mu sub 1 is the true mean saturated fat content in grams of brand D pizzas. Mu2 is the true mean saturated fat content in grams of brand PJ pizzas. And I am doing a two-sample T confidence interval at 90% for mu1 minus mu2. It is stated to assume all conditions are met, so I'm going to write that down. All right, now I need to find all of my, my means and my standard deviations from my samples. So I'm going to use the shortcut stat over to tests, and I'm doing a two-sample T interval. So this one down here, I have data in my lists. I have list 1, list 2, frequencies, you can leave them as is. My confidence level is 90%. Don't do pooled, and calculate. All right, so we have a lot of good stuff here. So first, I'm going to write degrees of freedom equal 32.757. Then I can write my formula for my, so we do need to write the formula for the confidence interval. We can't just write the confidence interval. So we have our first mean, 11.25, minus our second mean, which is 6.533, plus or minus the T critical level. Now the T critical value, again, is a little tricky when I have degrees of freedom that's not specifically on our table. So we've used the table to find the T critical values up until now. But the closest I can get to my degrees of freedom of 32.7 is at 30. I'm going to show you how to find the exact critical value. So T critical, we can use NVT in our calculator with area and degrees of freedom. It's a little tricky though, so pay attention. So we go to second, the vars button, and I can go to NVT. Now my area is a little tricky. It's not 0.90 because in a 90% confidence interval, draw this a little better. In a 90% confidence interval, I have 90% in the middle. And so if I want my T critical value, I want to know the area all the way down here. So area is that value all the way down. Now, if I have 90 and then I have 5% here and 5% there, then my area is going to be 0.95. So it's a little tricky, but the more you practice, the easier it gets. My degrees of freedom is 32.757. And then if I go down to paste, it'll give me my T critical value of 1.693. 1.693, and then times the square root of, I didn't write down my standard deviations. I got to go back. So go back to your 2 sample T int and all the way back down to calculate. Okay, so standard deviations, I have 3.193 squared divided by 20 plus 2.588 squared divided by 15. And then I can write my interval. So 3.0614 to 6.3719. All right. Make sure you write the degrees of freedom somewhere. If you calculated your T critical value that wasn't from this table, you probably want to write down how you got that as well. I am 90% confident that the difference in the true mean saturated fat content between brand D and brand PJ pizzas is between 3.0614 in grams, and 6.3719 grams. Don't forget your units. Now, part B asked me to determine, using my interval, if my interval supports the claim that the mean saturated fat content between the two chains is different. So remember, if they were the same, then mu1 would equal mu2, or mu1 minus mu2 would equal 0. So if 0 is not in my interval, then I can say that they're not the same. So yes, my interval does support the claim that the mean saturated fat content between the brands is different, since 0 is not in my interval. All right, and then if you're in my class, there is one more problem, but it's just kind of review, so I'm going to skip it in the video here. You can copy it in from our calendar, and that's it for today's lesson.